Stable isotopes in ice and water in glaciers are going to be important in our module in a number of different contexts, so I wanted to introduce you to them early on in the module. This context of the hydrological cycle that we're talking about today is a relevant one because isotopes illustrate nicely how big-scale hydrological cycle issues impact on tiny-scale issues within glaciers, right at the atomic scale. So what's an isotope? Well, isotopes are variations on a particular atom. In some elements, atoms occur with different numbers of neutrons in the nucleus, giving them different atomic weights. So, for example, in water, we have water, H2O. Water includes hydrogen atoms and oxygen atoms, but the hydrogen and oxygen atoms occur in different varieties. So, for example, hydrogen occurs with an atomic weight of 1, but hydrogen can also occur with an atomic weight of 2. When that happens, it's often referred to as deuterium, and we give it the symbol D. Oxygen, likewise, can occur with atomic weights of 16, 17, and 18. Now, chemically, these oxygens are all more or less the same, but physically or mechanically, these different weights, the different numbers of neutrons in the nucleus, give them different mechanical or physical properties. And likewise with the hydrogen, deuterium, chemically we can think of them as being the same from a glaciological point of view, but from a mechanical or physical point of view, they are slightly different. For today, I'm just going to talk about the oxygen isotopes. We'll come back to the hydrogen deuterium isotopes later on, but just to keep things simple, for now I'll just talk about the oxygen. Now, in natural settings, there's a typical ratio between how many oxygen 16s, oxygen 17s, and oxygen 18s that you typically get in a sample, and that's often referred to as standard mean ocean water, SMOW. Now, ocean water doesn't always adhere to this exact standard, but it's a standard from which we can measure differences. Now, typically, glaciologists pay more attention to oxygen 16 and oxygen 18 and less attention to oxygen 17, so we're going to ignore that for just now. And what we're going to be talking about throughout this session is the ratio between the number of oxygen 18 atoms and the number of oxygen 16 atoms in a sample. And this is often referred to as delta oxygen 18. Delta simply means the difference from the standard ratio that you'd expect. And delta oxygen 18 is saying, well, we're looking at the difference between this oxygen 18 to 16 ratio in our particular sample as opposed to what we'd have expected in a typical average sample. So standard mean ocean water itself would have a delta oxygen 18 value of, you can maybe work it out, since delta is difference from SMO, and we're talking about SMO, there is no difference because SMO is SMO. If there is a difference, it will be measured in parts per thousand per mil. It's just like percentage, but instead of being per 100, it's per 1,000. So the difference here would be delta value, delta oxygen 18, would be 0. But differences do occur in natural situations. I'll clear the board and then we'll have a look at some of those. So differences do occur because of fractionation. So suppose, for example, we had a bucket of water, and we'll say that to begin with our water had an isotopic composition equivalent to standard mean ocean water, but then we start evaporating from that parent water. Because the lighter isotopes, the oxygen 16s, are easier, more willing to get to that higher energy state, what tends to happen is that we get more of the oxygen 16s going into the higher energy state, leaving behind more of the oxygen 18s. It isn't that all the 16s go and all the 18s stay, but there's a fractionation, there's a slight division. So we get more oxygen 16s in the vapour and more oxygen 18s left behind in the parent water. That means that stops being standard mean ocean water, and because we've got more of the heavier isotopes left behind, more of the oxygen 18s, that has now become delta oxygen 18 positive. By contrast, our vapour, because it's got more of the lighter isotopes and fewer of the heavier isotopes, we refer to that as being delta oxygen 18 negative. The similar kind of thing happens in reverse if we're dealing with condensation or with freezing. So, for example, suppose I begin with a bucket of water again, standard mean ocean water, and I start freezing that water downwards from the surface. In these lower energy state frozen layers, the heavier isotopes are more likely to get trapped, whereas the lighter isotopes are more likely to escape and remain in what's left of the parent water. So here we have positive outcomes in the ice, and we have negative outcomes in that remaining reservoir of water. So as a result of these natural processes of evaporation or of freezing, and something similar happens with condensation, we're fractionating, we're separating out to some extent the heavier and the lighter isotopes. Now, I was talking about fractionation in buckets of water. We can think about exactly the same thing at a big global scale of the hydrological cycle. So if we imagine an ocean comprising water with our starting ratio, our standard mean ocean water ratio, but then we start evaporating water off that ocean, and then our vapour produces precipitation. But not all of the vapour falls out as precipitation. More falls out later on, and yet more falls out even later. Well, what's happening to the isotope values in there? Well, as we're evaporating water, evaporating from the water, then it stops being standard mean ocean water, and it will become delta oxygen 18 positive, because more of the heavier isotopes are being left behind, whereas our vapour is going to be delta oxygen 18 negative, because preferentially more of the lighter isotopes are going into the vapour, so it's depleted in oxygen 18s, whereas our reservoir is now enriched in oxygen 18s. So far so good. Now as that vapour precipitates out, what's coming out from the vapour is relative to the vapour, because of the condensation model, which is like the freezing model, what's coming out of here is going to be relatively positive or heavy compared with that cloud. So in other words, it's taking out some more of the oxygen 18s that it doesn't have many of to begin with. So the vapour is going to become increasingly negative. And the more we rain or snow out of that vapour, the more negative that vapour becomes. Until eventually, a long way from the source, after we've rained or snowed out some of the material that was in there, we can get very negative values for precipitation at high altitudes, inland, at low temperatures, precipitating snow onto the ice sheets. Now, without getting into the detail of that, my key point at this stage is simply this. The processes of fractionation of isotopes in water, vapour and precipitation lead to particular isotopic signatures in that precipitation. Now, as we'll see later, ice sheets forming on the land are built up of layer upon layer of that precipitation, and they preserve the isotopic signature which is imported into them from that atmospheric moisture. So the glaciers are giving us a record of whatever is going on in here. I've simplified this horribly, but I'm just trying to make this point that there's a connection between what's happening here at the global hydrological cycle scale and here in terms of actual atoms in the H2O that's going to make up the ice in our glaciers and ice sheets.